So to start this video off, I want to be extra clear that I'm making the assumption that you are comfortable looking at a structure, a Lewis structure, and being able to determine what types of bonds are present, and then being able to draw immediately towards the forces that are present. After that, I also expect you to recognize the level of strength of our intermolecular forces. So we'll real quickly kind of address some of those based off of the diagram that we've got here. So if we were to go through and look at an example structure real quickly, we'll pick two. We could look at water, nice classic example. When we look at the structure of water, we should be able to quickly identify that we have polar covalent bonds because we don't have a metal and a nonmetal, and then it doesn't fit our rule of our nonpolar covalent of same to same or carbon and hydrogen. So with a polar covalent bond, we would then translate that across to a dipole-dipole force. Once we have a dipole-dipole force, we could then ask ourselves, do we satisfy the conditions for hydrogen bonding? To have hydrogen bonding, we have to have a dipole-dipole, so good, and we have to have a hydrogen bonded to oxygen, nitrogen, or fluorine. And in this case, we do have that oxygen bonded to a hydrogen, so we do satisfy the conditions for hydrogen bonding. If we were to say to compare that to another structure, and we'll erase these real quickly, say something like ethane. So ethane, just two carbons with all the hydrogens. We need to, again, be able to really quickly go through and identify the bonds that are present. We're looking at carbon to carbon and carbon to hydrogen, both of those bonds, okay, because this is a little bit more complicated because we have two different types of bonds that we didn't have in water. Both of those bonds fit our nonpolar covalent classification for bond types. If we have nonpolar covalent classifications, that results in London dispersion forces. If we were now to compare these two molecules and say, well, which one had the stronger intermolecular force, what we're being asked to do is to compare London dispersion to our hydrogen bonding. Okay? The diagram shown below gives us that information, increasing strength of interaction. That increasing strength goes all the way around. A nonpolar covalent bond is a stronger interaction than anything underneath it. Okay? The polarity, which is also on here, just goes straight up. Okay, so polarity is better shown in the middle of the diagram, not on the edge like it is shown. Okay, so if we compare this London dispersion to hydrogen bonding is the stronger intermolecular force. What does that mean? Okay, so what that means is how we would apply that then to the physical properties. Okay, and this becomes one of the tricky concepts because when we think about these physical properties, we tend to go based off of strength of interaction. So we would go, oh, sodium chloride has an ionic bond, methane, nonpolar covalent, or water has polar covalent. Well, ionic bonds have higher melting points, so it must be that ionic bonds are stronger. And this is where the problem comes in. Our physical properties are not based off of bond strength, they're based off of force strength. And that's where you have to be careful. So you're using the bonds to help you determine the intramolecular attraction, but then you use that to determine the inter. The intermolecular is your physical properties. It's how those two different molecules interact with each other. So if we're going to look at sodium chloride, water, and methane, those are great compounds to look at. And if we were evaluating those, really what we're comparing is the ionic or intramolecular bonding for each of those compounds, H2O, and let's throw up our water, or not water, our methane, as covalent. Those forces, or those bonds, aren't what's determining the physical property. The forces that are generated from each of those are what are determining the intermolecular properties, okay, or your physical properties. So when we now go through and compare, the strength of an ionic bond is significantly stronger than hydrogen bonding, which is stronger than London dispersion. So when we're looking at these physical properties, you have to make sure that you're referencing the force. The forces are related to the bonds. You have to make that connection. Okay, so that describes our melting points and boiling points, which are somewhat easier to interpret, though there are weird exceptions that'll come along with those, and we'll poke at a few of those. The next part, solubility. Okay, solubility is going to become much more difficult or challenging to deal with because solubility is comparing two different molecules and the forces within them. Okay? We now have to decide, are those forces the same? So one of the things that you get for solubility is this like dissolves like. Well, like what? Like forces. Again, back to the forces. So if you're being asked to explain something about physical properties, you better not be using the word bond because bond is irrelevant. Not as relevant. Forces is what's dictating your interaction. Okay, so you have to reference those forces. We could look at vapor pressure. This is really just a copy over slide from when I talk about it in Chem 130. We don't really stress about vapor pressure in OChem, so don't worry about it, but you could apply it similarly out. If we go through and look at our reactivity, okay, well, reactivity is ultimately going to come back to our forces as well. Because if we go through and look at, say, our methane versus our water, we could actually use these intermolecular forces to predict something about that reactivity. Methane generates London dispersion forces, which are very, very, very weak, which means it doesn't need to interact with any other molecule. So what would be its reactivity be? Well, reactivity is literally interacting with another molecule. It doesn't want to. Right? So we might expect the reactivity of methane to be very, very low. And sure enough, it is. If we go through and look at a molecule like water with hydrogen bonding or dipole-dipole forces, however you want to label it, those forces are much stronger. And they're stronger because they're trying to cancel out some of that partial charge that's being generated in those weaker bonds. Okay? Because we're generating that charge, now that molecule looks out to something else to stabilize the charge. Looking out to something else, there's a reaction. So water becomes much more reactive than methane. Okay, so we can use these forces to help us predict something about the reactivity of the overall functional group. And as we slowly bring in more functional groups, what we're going to do is look at that polarity of those bonds to try and predict something about their reactivity. Okay? That's cool. Okay? So whenever we're talking about reactions, look back to that bond and force aspect and try and use that to help you interpret where you would go from there. Okay? With that, let's take a look at our melting points. So our melting points and boiling points is a measure of the energy necessary to cause a phase change. Okay? So if we were to draw this out kind of pictorially, what we're looking at is solids, where they're all closely packed, transitioning to liquids, where now there's a little bit more space, a little bit more movement. It's nowhere near as regular as a shape. I can't draw it very well. Digital things draw it much better. Or gases, where they're all super spaced out. And when we're looking at our melting points, what we're talking about is breaking each of these forces in between. So sometimes you'll hope the bonds are breaking. You aren't breaking a bond, okay? To think about that in another way, if we're going to say break the bond when we melt ice and turn it into liquid water, what you're saying is that you end up with hydrogen and oxygen separated. That ain't true, okay? It's still H2O. It's the distance between those individual molecules that changes when you change phases. That's an intermolecular attraction. That's a force. So when we're talking about our phase transitions, these are forces that we're breaking. Okay? So to go from that solid to that liquid, I have to put in enough energy to break that force. Okay? The resistance on that phase change is the strength of that attraction. Okay? So that attraction is going to resist moving into the liquid state. Okay? And that's going to help us there. Okay? Or we can take advantage of that. That's going to give us a temperature that we could then say correlates to the melting point for that substance. And because most substances have different intermolecular forces because they have different bonds, we could then characteristically identify a compound based off their melting points. That's kind of cool. When we go to the liquid to the gas, it's a little bit more complicated. Okay, remember, you broke apart a lot of those intermolecular forces. They're still there, they just aren't quite as common, and they definitely aren't as organized. Okay, so that next transition is still going to be an energy necessary to break those formal attractions, because when we move to the gas, there is no attraction between those. We don't have any intermolecular forces. Okay, but we're also breaking something else. We're breaking an external pressure. Okay, we're breaking atmospheric pressure that's holding the liquid together. So when we transition on boiling point, we're looking at really two different things: a little bit of intermolecular forces and atmospheric pressure. This is why when you look at boiling points, they drastically change depending on atmospheric pressure. Okay, the boiling point of water at altitude, okay, is significantly lower than it is at sea level. Right? And that has to do with this atmospheric pressure holding the things in there. Okay? The biggest contributor for all of these things, though, is going to be intermolecular forces. So when we talk about boiling points and we talk about melting points, either way we do it, we're really going to ignore, for the most part, atmospheric pressure, at least in this class. And what we're concerned about is that intermolecular force. Right? How do I cause that intermolecular force to break? When we transition from the solid to the liquid, I have to break a whole lot more of them, okay, which means it requires more energy to get that to kind of break apart. Okay? So if I'm going to look at higher melting points or boiling points, well, a high melting point is going to have a lot of intermolecular forces within it. Well, yeah, quantity contributes, okay, but also the strength. So if I have, say, sodium chloride, that has ionic forces. Compared to methane with London dispersion forces, well, ionic is a stronger force, so that's going to require more energy to pump into it to cause it to break apart. And that's why we see a higher melting point for ionic compounds. Okay, the same thing's going to translate to our boiling points. Okay, we're just looking at a slightly higher level of it. Okay, so we don't have to stress a whole lot about differences between melting points and boiling points, because really it's the same principle. Okay, the stronger the force, the more energy it takes to break it apart. So you need to be able to look at a formula and say, hydrogen bonding, strong force, I'm going to expect an elevated melting point and boiling point. Okay, is it only the strength of the force, though? Okay, so the arguments that I like to use in this case when we're thinking about looking at forces and things along those lines is, let's look at it as, because apparently I'm confrontational, let's look at it as like a fight. Okay, you're going into a fight and you see two opponents. Okay, you see The Rock, okay, big, strong, Dwayne Johnson, big, strong guy, versus me. Okay, he's bigger significantly, and if you had to choose which way you were going to fight based off of that strength, you would probably pick to beat me up. It helps that I'm also a teacher, and you're like, dude, you made my life miserable. The Rock entertained you. Okay, so you would choose me. So you're looking at the strength of those. Okay, but are there other things that could come into play? Okay, so yeah, you could try and fight The Rock or me. Okay, but I've got, it's probably not true, but let's just say it is true. I have more friends than The Rock, which means when you're going up in that fight, you're going to fight The Rock or me and 20 friends. Okay, you might be able to take me out, but the other 19 friends probably going to pummel the crap out of you. So you might now choose to fight The Rock and hope you can dodge fast enough, kneecap him or something like that, so that you could win. So when we're looking at these physical properties, it's not just strength, it's also an amount. Okay? That amount can make a really big difference in your melting points and boiling points. So our first line, strength, then we have to nuance. Okay? Do we have to nuance further? Sometimes. Okay? And a lot of that is just thinking about that process and trying to come up with ways to nuance that difference. Okay? The textbook goes in and explains some of that, and we'll see some examples here in a little bit when we're looking at those melting points and boiling points. Okay. The next one, solubility, the ability of two substances to mix homogeneously. Okay. Well, what's going to help that? If we're looking at how they mix, we're talking about two different substances. So we could say a bunch of red circles with a bunch of blue circles, or a bunch of blue stars. Okay, if I were going to attempt to mix these, which ones would be more likely to mix? Okay, well, we might expect that the red circles with the blue circles would mix, and with the stars, it would not. Okay, and the reason behind this is the similarity of those forces. Okay, if we look at the connections between these, okay, those forces are similar in the same shapes, our circles. As soon as we move into stars, well, now that changes the shape. Okay, that changes the shape, and that changes how those things interact, and that's going to change the solubility. Okay, and typically it changes it to make it less soluble. Okay, if we're going to look at real-world systems with intermolecular forces, well, we're going to apply the same kind of principle. We're looking for similar forces. So if I'm going to look at how I could mix, let's pick a couple examples here. Water, how water could mix with ethanol. Unfortunately, we get a lot of ethanol usage probably in our organic chemistry classes just because trying to drown out some of the misery. That is not a good option for the record though, so you should just study differently. CH3, CH2, CH3. If we were now trying to decide should these things mix or not, what we want to do is again look for the similarity of forces. One of the things that could help is if we repackaged water to be HOH, and this is going to help to call out that we have a similarity in the structures. This is hydrogen bonding all the way through, whereas in the bottom case, we don't have that hydrogen bonding, we have London dispersion. So when we make our comparison between those, well, hydrogen bonding is similar, hydrogen bonding is similar to hydrogen bonding, and hydrogen bonding is not similar to LDF, which means not mixed, and it mixes. Okay, so that's the simplest level that we're looking at. Okay, are there other things that could get in the way? Okay, well, isn't this section all nonpolar? Okay, isn't that all London dispersion forces? Yeah. Okay, but hydrogen bonding is so strong that it overcomes those London dispersion forces. Could we invent a molecule that would counteract that? Yes. Okay, and it isn't that hard to go through and do, because we could do our HOH, and now let's throw in CH2, 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 CH2. Really all I'm doing is copying and pasting the same phrasing over and over as I rewrite. Okay, now there's a lot more London dispersion forces. Those London dispersion forces will overcome the hydrogen bonding. So we get this threshold. Where's that difference? Where does hydrogen bonding outweigh the importance, okay, on those fights? Okay, and if we think back to the fight examples that we were using in the past, the rock versus me, if I had 20 friends, you're probably going to fight the rock. But what if I only have one friend? What if I have two friends? Okay, what if I have one friend with a gun? Okay, all of those things change how it interacts, which kind of goes to say that when we're looking at our intermolecular forces and how they apply to both melting point and solubility, it's a little bit of guesswork. Okay, our guesswork works really well. Okay, it usually comes out about 80% of the time. Then we have to change our theory a little bit. We start with just the strength of the force, then we say, well, we have to include an amount. What's the amount? A little hand wavy, but we got to come up with some a hand wavy approximation on it. Then what's the shape of them? Okay, maybe I have 20 friends, but they're all I don't know, mutants. Like their heads are attached in the wrong spaces. Right? You might be like, well, you may have 20 friends, they aren't going to do anything to me because they can't even walk. Okay, so that doesn't really count. Okay, so the shape can also have a factor within this. And really, we only experience that when we go through and test these things out and see them. When it comes to actual exams, we tend to not test on the exceptions. We tend to test on the larger pictures. And those larger pictures, strength of the intermolecular force and amounts. Those are going to be the big ones. Okay? So how does this all come together? Well, not quite yet, because what we want to do is bring in, when we're looking at our solubility, is some terminology to go with it. When we're talking about solubility, we're talking about dissolving anything in a liquid. In OChem, it's solids into liquids. Okay? In most chemistry classes, it's actually going to be solids into liquids and not gases into liquids, because gases are harder to work with. Those liquids that we're dissolving everything in, we call our solvent, and our solute is what we're putting into it. Okay, so our solvent, we could now come up with terms to help describe it. And you notice I started to actually drop some of these terms already. Okay, I argue that we shouldn't be using these terms, that we should be using our intermolecular forces. But these terms appear, and so we have to have some kind of understanding of what they mean. So the first kind of definition that allows us to differentiate this would be polar and nonpolar. And really what we're trying to say between polar and nonpolar is that we're trying to say that we have polar, ionic, hydrogen bonding, dipole-dipole, molecules. So molecules that would exhibit those intermolecular forces are polar, and that our nonpolar substances would be ones with London dispersion forces. Those aren't really fair because we got 3 polar and only 1 nonpolar, so it'd be like, that's really easy. It turns out that, remember, this is a gradient. These aren't absolute values. You could have a dipole-dipole force that is relatively weak. Okay? So we could encounter a system where we also get some dipole-dipole in the nonpolar category. This would kind of go to say that if we're looking at a dipole-dipole molecule, we should be careful classifying it as polar or nonpolar because it's on that threshold. It's a borderline case. Okay? So we would have to look at it a little bit more carefully. But this is largely what we're trying to do when we talk about polar and nonpolar. We're trying to simplify that system. Okay, so we can call a compound nonpolar instead of saying it has intermolecular or London dispersion intermolecular forces. Okay, so it's just a way to kind of subclassify it. The problem with this is polar and nonpolar isn't exactly as simple as the intermolecular forces that make them up, right? Which we already saw with the dipole-dipoles. They're gradients. Right? Sometimes it's a little bit more one way, sometimes it's a little bit more the other way, and we can see these kind of shifts. So we have to be very careful when we go through and assign things as polar and nonpolar. And I would argue if you're being asked to explain something, you'd better not use the word polar and nonpolar because they don't explain appropriately. Okay? And for those people going, but the internet says, I know, the internet is full of crap a lot of the time. Don't use polar and nonpolar. Use your intermolecular forces when looking at an explanation. Okay? You'll also see a further subcategorization within this, and we encounter protic versus aprotic. Well, why do we need this protic versus aprotic? Well, that protic versus aprotic really had to do with what forces we said were showing up in polar. Well, in polar, we had 2 types. We had hydrogen bonding, and we had dipole-dipole. Okay, well, the hydrogen bonding attraction is a stronger attraction than the dipole-dipole. How could I nuance that my polar hydrogen bonding solvent is different than my polar dipole-dipole solvent? That's where we introduce the term protic. Okay? Hydrogen bonding, if we think about that, is in reference to hydrogen. Okay? And the reason we're getting hydrogen bonding as an interaction is because we're bonded to an oxygen, nitrogen, or fluorine. Those being the 3 most electronegative elements, which means the electrons in that bond go towards the oxygen, which means we're seeing a very large partial negative and a very large partial positive. Okay, so let's push that to the extreme and say really what we're looking at is an H+. Well, can you name H plus any other way? What would make up H plus? Well, hydrogen has one proton, okay, and one electron. Doesn't have any neutrons, so it's just a proton and electron. But it's H plus. Get rid of the electron. What is it made of? A single proton. Protic is in reference to hydrogen bonding. It's a direct reference to it. So if you're referencing a solvent as being protic, you're saying it has hydrogen bonding. Why use the protic term instead of hydrogen bonding? History. Okay? We've decided that we want to call things or classify things as protic solvents as opposed to hydrogen bonding solvents because somebody just decided that that's our nomenclature system. Okay? Which means if we go through and look at our intermolecular forces again, we've got ionic, hydrogen bonding, dipole-dipole, and our London dispersion forces. Okay, well, protic by definition meant hydrogen bonding. Okay, so we've got protic falling under the hydrogen bonding category. It also, by definition, is going to be polar because that's how we get hydrogen bonding. So really, a hydrogen bonding solvent is going to be polar protic. Okay, the next part. If we move to a dipole solvent, the dipole-dipole will likely be polar. Okay, it won't be protic. Okay, because if it was protic, we'd call it hydrogen bonding. So we could call it polar aprotic. That aprotic now tells me that I don't have hydrogen bonding involved in it. Why didn't I just say it was hydrogen bonding versus dipole-dipole? Irrelevant. That's just the way we work. Okay. The next part on this is, remember that dipole-dipole force could split in such a way. Did I want to do that? No, I didn't. Okay, so our dipole-dipole force is now polar aprotic. Our London dispersion, okay, is not polar, so it would be nonpolar. Okay? It also is going to be not protic, okay, because protic meant hydrogen bonding. So it would be nonpolar aprotic. So really the terms that we're coming up with are just another way to label the forces that made them up. So we have the forces that we've already discussed, and then we also have solvent terms. Why do we invent two words that mean the same thing? Talk to an English major, not to me. Okay, but that's ultimately what's happening. For the keen eye, you might be like, but dude, you didn't mention ionic. Why is ionic not classified as solvents? Well, think of your ionic compounds, sodium chloride. That intermolecular force is so strong that when we look at that substance, it is very typically a solid. To get it into a liquid, we have to achieve extremely high temperatures, 900 degrees Celsius. Why is that a big deal? Well, what happens when you put an organic substance into 900 degrees Celsius systems? They get destroyed. Okay? So the ionic solvents typically don't fall into our standard box categories of polar protic, polar aprotic, or nonpolar aprotic. Okay? We tend to ignore them. Okay? So our ionic substances don't really fall in that system. Okay? But this is where our classifications go. There are things known as room temperature ionic liquids. Okay? They do exist, and they tend to fall in kind of a weird category of a pseudo-ionic and a pseudo kind of dipole interaction. And that's really neither here nor there, but it is kind of interesting if you were interested in looking at solvent effects. Okay, so we will see these terms pop up. I will say that if we go through and evaluate these terms, polar protic is a bit redundant. If it's protic, it's by definition polar. So we could call a hydrogen bonding solvent a protic solvent. Polar aprotic does become important, okay? Because that polar could suggest hydrogen bonding. By throwing in the word aprotic, it becomes important. So, or it differentiates it. So calling it polar aprotic is useful, okay, and is commonly done. When we move to the LDF forces, it by definition will be aprotic, and so we could typically refer to those as just nonpolar. Okay. Again, for the keen eye, you might be able to go through and say, well, couldn't you have just said protic is hydrogen bonding, aprotic is dipole-dipole, and LDF is nonpolar? Yeah, but we don't. Okay. The way we go through and do it, hydrogen bonding is protic, dipole-dipole is polar aprotic, and London dispersion is nonpolar. Again, remember, gradients, these aren't perfect. What do I mean by not perfect? Well, that would be helpful if we looked at some examples. So we've got a bunch of structures down here. You should be able to go through and classify them according to those terminologies that we just did. Okay? To help you with that, I'm going to go through and do two of them. Okay? The two I'm going to do this guy and this guy. So when I go through and look at those, what I should be seeing at this point is, because I've been doing lots of Lewis structures, recognize that those are all carbon and hydrogen, and those would all lead to LDF forces. I also see that OH, and that OH should be hydrogen bonding. When I look at this molecule, I'm going to see that hydrogen bonding, and I'm going to immediately call this a protic solvent, okay? Because it does have that. It also has this nonpolar aspect. This solvent has two components to it. Which one's most important? Probably the protic, okay? And that protic has to do with hydrogen bonding and all that other fun stuff. So this solvent would get classified as a protic solvent, okay? If we move to the last one, again, because I'm good with Lewis structures, I'd be looking at that, all carbons and hydrogens. That's going to be LDF forces. The LDF forces calls me as nonpolar. This one becomes a nice easy one, because there's no other force to evaluate, and this becomes a nonpolar solvent. Cool. Okay. Last question we could throw in on this, would I expect these two to mix? Well, no. One's protic, one's nonpolar. Those don't make sense to mix because they're different forces and they're different solvent terminologies. Okay. Which gets us to a big fun quiz, so we'll see some questions pop up on this. What I want you to be able to go through and do is multiple things, okay? So officially questions 1 and 2, because this would be a quiz we do in class, I want you to go through and rank highest to lowest melting points for your solids and then for the liquids. For the liquids, officially, you'd be doing boiling point. So what do I mean by that? You should be able to tell me for the solids, and this isn't the answer, that 3 has a higher melting point than 2, which has a higher melting point than 1, which has a higher melting point than 4. Ta-da! That's the ranking, okay? Or that would be a ranking. So you should be able to go through and determine melting points. You should do the same thing for the liquids. The last question becomes challenging. Match pairs that are most likely to mix, okay? This one is really challenging because there's more than one answer for pretty much everything. Okay? So what do I mean by coming up with a matched pair? Well, I would go through and say, well, structure 1 has the most similar forces to structure A, which means I would expect as a mix, because we're looking for a homogeneous system, 1A would result in a homogeneous mixture. That's what that explanation would be. Okay? Again, I'm not saying that's correct. In fact, I will tell you right now, it's wrong. Okay? So you should be able to go through and do these pairs. For those of you being like, oh dang, that's a lot of work, I don't really want to do that, I'll probably ask it as a test question. It's also probably a good thing to throw into a discussion board post so that you can get credit for engaging in the material. Okay? All good things. Application. What becomes important behind being able to come up with these classifications? If we go through and look at an individual reaction, okay, so what we're looking at first up here is a reaction. We've got reactants, and we have products. To allow this reaction to occur, the reactants must interact with each other. Okay? For them to interact, they need to be in the same phase, because that's going to speed the attraction. Well, if we go through and look at these, that first substance, fairly nonpolar, LDF. The chloride, being negatively charged, is ionic. Well, that now becomes a challenge because those are very different intermolecular forces. So I want to pick a solvent that's somewhere in between that can help bring those two into the same phase. So I might pick a, let's go with polar aprotic solvent. It needs to be aprotic to help pull in that LDF molecule, and it needs to be polar to help pull in that ionic solvent. If I picked a protic one, great, the ionic comes in, the LDF doesn't. Okay? So I want to choose my solvents very, very carefully to help facilitate a reaction. The next layer that can go on top of this is if we look at the bottom case, this would be a reaction. This bottom case is now discussing it as a mechanism. Okay? In this mechanism, I'm saying that the iodide has to leave the structure. Okay? That's why it's as a product floating off on its own. As it does so, it forms a carbocation. That would be a compound that is missing its octet, highly unstable. Okay? If it's unstable, would the reaction occur? Well, no. Okay? So my solvent is not only going to have to facilitate bringing these two together, but I now have this second issue that I have to worry about. Okay? I need to make sure that that product is as stable as humanly possible. Okay? Because if that drops down in energy, now the reaction becomes more likely. So picking a solvent isn't just as simple as mixing your reactions or your reactants. It's also looking at the mechanism of how that reaction occurs. Okay? That's really neat. And it also gets really kind of dicey and difficult to nuance out. And usually what it turns into is just bulk memorization, okay? Which is okay, but we have the power to be able to run an explanation and explain how and why it's working, okay? Solubility is also not super straightforward, okay? Does it dissolve in water? So if we were going to go through and look at a dissolving in water, first it might be helpful to have our structures, H2O for our water, our ethanol, CH3CH2OH, chloroform, CH3Cl, acetone. Sorry, I'm modifying how I'm drawing each of these structures out. I do kind of apologize. And diethyl ether. Okay, we would need to go through and evaluate similarities in intermolecular forces. Okay, if we're going to go through and explain, okay, methanol or ethanol, yes, they have similar intermolecular forces, hydrogen bonding. It works. Okay, chloroform. Chloroform is a dipole-dipole interaction due to that carbon-chlorine. It turns out that dipole-dipole is not strong enough to equate to water, so no. Okay, we move to acetone. Again, we have a dipole-dipole interaction with that carbon to oxygen. But again, we have lots of these non-polar forces out at the ends. So we might say, well, if chloroform didn't do it, acetone shouldn't. Acetone does. Okay. Why does acetone dissolve? A lot of that has to do with that polarity of the carbon-oxygen bond versus the polarity of the carbon-chlorine bond. The carbon-oxygen bond is more polar because difference in electronegativity. Okay. That's what's facilitating that. If we throw in our diethyl ether, you might be like, okay, well, dang, I've definitely got a hold of you now, Mike, because you said carbon to oxygen was polar enough. This is carbon to oxygen. It's going to be soluble. Nope, no, it's not. Okay. What the hell? Okay. So a lot of these things we have to nuance out. So there are big differences. When we looked at the acetone, that was on one axis, okay, for that polarity. When we look at diethyl ether, that's on two axes. Okay. So we're spreading out that polarity, which means we do have that large difference, but we've also spread it out. The other aspect behind this, these are sigma bonds, okay? And in fact, all of these are sigma bonds. And why does that matter? Well, what can sigma bonds do? They can freely rotate. And that free rotation can go through and bring these nonpolar parts, these LDF parts, and cause them to rotate down to block water from interacting with that oxygen. Okay? So the structure itself flips and mutates to prevent the solubility. That's nuts, okay? But that's what it does. Okay? Last thing that we'll look at before I'm done with this, because this is way longer than I wanted. What could be done with our interactions? We can look at, basic simple things that we've already seen in our life. Okay, salt dissolves in water, but oil doesn't. Well, differences in intermolecular forces. How does soap help water dissolve? Well, soap creates micelles. Soap is a molecule that is extremely polar at one end and extremely nonpolar at the other. Okay, and it's in one molecule. That one molecule means the polar part can interact with the water and the nonpolar part can interact with the oil, which allows them to mix. In that mixing process, what we end up forming are these things known as micelles. The micelles dissolve the oil, as I go back and forth with drawing or not, dissolve the oil on the inside and allow water to interact on the outside. That forms these little droplets that allows us to wash the oil off of our hands. And we might say, well, cool, so you can wash your hands, big deal. Okay, well, if you bring enough of these things together, you can form liposomes. You're like, why do I care about liposomes? You clearly haven't taken enough biology, because liposomes are things that happen in biology. Bilayer sheets, which is really just a liposome on a grand scale, because a bilayer sheet ultimately does loop back around itself. And again, why? That's cell walls. Cell walls are due to these intermolecular forces. So when we think about how to break apart, viruses, what we're concerned about is that bilayer sheet and what intermolecular forces are on the surface that change how things can pass through them. All of that is based off of intermolecular forces and these interactions. And that is pretty freaking cool. Okay, with that, we're done. Thanks for listening.